deep field dynamics model for granular object piles manipulation. Granular materials, such as beans, nuts, and sand, play a significant role in both everyday life and industrial applications, making it crucial for robots to accurately model and manipulate them in various scenarios. However, the complexity of granular materials, with factors such as size, shape, friction, and contact mechanics, poses a challenge for direct modeling. To tackle this problem, recent efforts have focused on deep latent dynamics models using pixel-wise input. However, these models often struggle to capture accurate dynamics due to the lack of inductive biases. Alternatively, physics-inspired concepts such as particles provide strong inductive biases but suffer from scalability challenges, as their memory and computational costs grow with the number of particles, making them impractical for granular manipulation. To address these challenges, we propose a novel approach using field-based representations for modeling granular object piles. By leveraging the insight that interactions between granular objects are dominated by local friction and contact, and are also translationally equivariant, we propose a fully convolutional network that employs a unified density field-based representation of both states and actions. By using differentiable rendering, the dynamics model is fully differentiable and enables us to integrate learned field dynamics with gradient-based trajectory optimization methods, such that our methods perform complex motion planning tasks, including pile pushing while avoiding obstacles simultaneously. We evaluate our approach through various simulations and real-world scenarios, demonstrating the superiority of our field-based model in terms of efficiency and accuracy compared to existing approaches. Moreover, our model shows generality by successfully transferring to different environments with varying object and pusher shapes in a zero-shot environment. Thank you.